Geometry, Lesson 7.4, Special Right Triangles. The first special right triangle that we'll be talking about is the isosceles right triangle. By isosceles, we mean that we have two congruent sides, which creates a situation of two congruent base angles. Because this is a right triangle, both of these base angles must be the remainder of 180 degrees, so they will be 45 degrees each. This is also known as the 45-45-90 triangle. In an isosceles right triangle, there's a special ratio that we can learn, and this will benefit you because if you know the length of even one side of a 45-45-90 triangle, you can solve all the other sides. So if each leg has a length of 1 unit, which means that AC equals CB equals 1, then using the P theorem, you can say that the hypotenuse AB squared equals AC squared plus CB squared. We'll substitute those values of 1 into AC and CB, and 1 squared plus 1 squared, and remember that 1 squared is 1, is 2, and if we want to solve for AB, we take the square root of the 2, and that's as far as we'll go. So the hypotenuse will be square root of 2. This gives us a continuous ratio of 1 to 1 to square root of 2. Any value that you have that you replace for a leg or for the hypotenuse, you can use to solve for the other two sides. So let's make this a formula and get down to the basics. Instead of a 1, we're replacing the ones with x's, and remember back in the last slide, this says square root of 2, but it's really 1 square root of 2. So here we have x, x, and x square root of 2. This leads us to the 45-45-90 triangle theorem. If the length of the leg of an isosceles right triangle is L, then the length of the hypotenuse is L square root of 2. So this is what they're saying right here. L square root of 2. The sides will then be in the ratio of 1, 1, and square root of 2. Let's do an example. Find exact values and decimal approximations for the lengths of AC and AB. I put down, remember, the ratio 1, 1 square root of 2. You should have this on notes with a picture of the triangle. That way you'll know which equations to use for these problems. So we're going to begin with this triangle, and I've added some different values to it. Whenever I'm working on these triangles, I like to go ahead and write in the ratio right there. That just makes it more visible and easier to solve. So the side opposite the congruent angles are congruent. So we have 45 and 45, so side BC is 3 centimeters. That means that side AC will be 3 centimeters also. Now we're going to apply the theorem, which means that we take this side length and for the hypotenuse make it square root of 2. So if the side length is 3, it's 3 square root of 2. And then we use a calculator to find the decimal approximation of square root of 2 times 3. Now, depending on what your calculator it will be how you work this. On my computer's calculator, I have to do 2 square root times 3, and that will give me my answer. And we're going to round to tenths. So the number next to the 2 on the right is a 4. If it was a 5 or larger, we would move this 2 to a 3, but because it's not, we're going to keep the answer 4.2. And we have approximately 4.2 centimeters. Now when you're doing these problems, if it's not an exact answer, you need to use the approximation symbol. Example 2. We have another 45, 45, 90 triangle. So I've gone ahead and written in the ratios. And in this one, we don't know the short and long side lengths, but we do know the hypotenuse. So find the exact values and the decimal approximation for the lengths of the legs. So the hypotenuse will equal leg square root of 2. So let's fill in our known value, which is 12, and it's 12 equals leg square root of 2. And I should go ahead and do this right now to make sure I don't think this is a 1. And we have leg equals, and to get to leg, we have to divide both sides by square root of 2. So here's our formula at this point, or our equation at this point. And leg equals 12 divided by square root of 2. There's this thing in algebra that they do in our country. This is not true for all countries, but they like us to rationalize the denominator. They don't like a square root in a denominator. So this is something from algebra that you did, and this is a review. We need to remove the radical sign from the denominator by multiplying this equation by the number 1. And remember, when you multiply by 1, it's any number divided by itself. So we use square root of 2, and square root of 2 times square root of 2 is just 2. And on the numerator, that will leave us with 12 square root of 2. As you're going along with these problems, you can actually skip this step if you realize that 12 divided by square root of 2 will look like this equation, 12 square root of 2 divided by 2. Now at this point, you need to take a look. Is there anything I can simplify? Can I reduce? And sure enough, 12 can be divided by 2. You cannot take the square root and divide it by this denominator. So 12 divided by 2 is 6. 6 square root of 2 feet is the answer. And we can, if we want to, use the calculator to find a decimal approximation. So this would be 6 square root of 2. So 2 square root 6 equals nothing. I did it wrong. Let's try again. 6 square root times 2 equals 4.89. The 9 is greater than 5, so we'll answer 4.9 centimeter or feet. So it'll be 4.9 feet. And this is what our answer will look like. L is approximately, oh, I just messed up. This should be H. And when I do these, I actually put HYP because I get confused because of the fact that we've been using height, and we call that a little h, and this is actually a hypotenuse. So if I were to have done this problem not using the book's example, I would have changed this to XY right away. Might make it a little simpler. Let's move on. Special triangle number 2. This is a 30, 60, 90 triangle, and it's an equilateral triangle. And the way that we solve an equilateral triangle is to drop an altitude that will bisect CB. So AD bisects CB, and consequently 2 congruent right angles are formed. In this instance, we'll have a different ratio than the 45, 45, 90. If this segment DB, which is half of the segment of the base here of the triangle, equals 1 unit, we already know that AC equals CB, and they are 2 times the short leg of the right triangle. So AD squared plus DB squared equals AB squared. So AD squared plus DB squared, long leg plus short leg, equals the hypotenuse squared. And if we substitute our known values, AD squared plus 1 squared, which was DB, equals 2 squared. 1 squared is 1. 2 squared is 4. 4 minus 1 will be 3. AD squared is 3, so AD, the height, will equal square root of 3. And we can also call this altitude, but it's the height of the right triangle. Now if we go ahead and substitute variables for that same problem, these are all the things that we have known about this triangle so far. We know that DB, the short leg, is x. The long leg will be now x square root of 3, and the hypotenuse will be 2x. So if that's confusing to you, what you need to do is look back and forth between the last slide and this slide. Perhaps put them on your paper next to each other, and you can see that we're just replacing the 1 in this slide with x. So we have the 30, 60, 90 triangle theorem. If the length of the shorter leg of a 30, 60, 90 triangle is x, then the length of the longer leg is x square root of 3, and the length of a hypotenuse is 2x. The sides are then in the ratio of x to x square root of 3 to 2x, or you could also say, for using the numerical values, 1 square root of 3 and 2. So have that on your paper always when you're doing these problems. And let's do an example for a 30, 60, 90 triangle. So I've gone ahead and put in our ratios. We do know that we have a long leg of 12 centimeters. So we're going to find other sides according to that leg. And the difference between the long leg and the short leg is the long leg is divided by square root of 3. So to get x, you have to divide by square root of 3. So 12 equals x square root of 3. X equals 12 divided by the square root of 3. We rationalize the denominator, and we end up with 12 square root of 3 over 3. 12 divided by 3 is 4 square root of 3 centimeters, which is approximately 6.9 centimeters. Now we need to solve for the other side. So we have x, which is 6.9. We have 12, and we know that z, the long leg, is 2 times the short leg. So you can do this a couple of ways, but it's more accurate to start from the beginning and work this out, because the short leg is an approximate number. I wouldn't double this. This could give you the wrong answer. So z equals 2 for 4 square root of 3, which is 8 square root of 3, which is approximately 13.9. Now, we have another way to solve for the area of an equilateral triangle. This is a formula that you will use over and over and over again, and it needs to be placed in memory, but I find with students that it's a very confusing formula. So we'll walk through this, and if you need to, we can go through this in class. First and foremost, and let me get my highlighter here, we have 3 congruent sides because it's equilateral, and we're going to call these sides S. Remember that we have an altitude that's been dropped that divides this base in half. That means that the S is divided in half, so that makes it S squared. If you were to add, S divided by 2. If you were to add S divided by 2 to S divided by 2, you would end up with S. So, we also have the ratios that we know of, and the ratio for the long leg, if you remember, let's go back and look at it. The ratio for the long leg is x square root of 3. So the x would be s, and it would be square root of 3 divided by 2. So this s divided by 2 becomes multiplied by square root of 3. And it seems there are different ways you could write this. You could have the s before the square root of 3 over 2, but in books this is the way you will always see it. It will always be square root of 3 over 2 times s. Okay, so that's actually the long leg. So these are the pieces of the triangle, and you'll be using these pieces. So you should make a picture of this and go ahead and just mark it this way. At first it won't be intuitive, but as you go along to use it, you'll get the idea. So the area of an equilateral triangle is square root of 3 over 4 times the square of the length of one side. That square root of 3 over 4 is actually derived by using all of these pieces of this triangle. I'm not going to do it here on this video, but we may do it in class if we have time. So take this formula and just write it down, and this will be the area of an equilateral triangle. Now you can also solve by adding two triangles together if you get in a pinch, but this will be much quicker, and this will be the area that you need to use. Let's use one of these formulas for the area of an equilateral triangle in an example. So packaging shaped as a regular triangular prism provides excellent protection for shipping large prints. If each side of the prism is 5 inches wide, what is the area of each cap of the prism? I'm not going to review the shape at this point, but needless to say, the ends or the bases of this prism are equilateral triangles that are 5 inches on one side. So a side is 5 inches. So let's look at our formula and replace the s with 5. So we have square root of 3 divided by 4 times 5 squared. So 5 squared is 25, and they've now moved the 25 over here on the top of your numerator. It was actually there already. It was just over 1. So 25 square root of 3 over 4 inches squared, and you can use your calculator to approximate, and you'll end up with 10.9 0.8 inches squared. Your homework is numbers 1 through 16, 19 through 23. 25 I put down as extra credit, and what I mean by that is it's a very difficult problem. If you want credit for this problem, what you need to do is work the problem out, but show me every step of your work to get credit. And last problem to do is number 30. So let's go on to just a couple of examples to give you some idea how the homework will go. Homework examples, we have number 6 on page 321. And we have, just by looking at this triangle, you should be able to identify this is a 30, 60, 90. So find the exact lengths in each triangle. Use example 3. I wrote that in there. That's the example that is the most similar to this. And I also put down the ratio. So they've made this very complicated in this example, but they're doing it to help you think about what you're doing. So the short leg, which is P, equals the long leg, which is 15, and the long leg, remember from these ratios, is the P square root of 3. So it will be 15 divided by square root of 3. Remember, it's not 15 times square root of 3. To get from the long leg to the short leg, we have to divide by square root of 3. So now we can say that P equals 15 divided by square root of 3, rationalize. We have 15 square root of 3 divided by 3, which is 5 square root of 3. Now we need to solve for our hypothesis, which is Q. Now Q equals 2 times the short leg, which is P. So 2 times 5 square root of 3 equals 10 square root of 3. Now you don't have to do all this stuff with the short leg and the long leg. You can just use P and Q, but it will help you to see this in the examples so that you know what portions of the formula you're using. Number 13 on page 321, determine whether a triangle with the given side length is a 45, 45, 90 or a 30, 60, 90, or neither. I went ahead and put the ratios under those triangles so we can see them, and this is the problem. It's a 7, length of 7 square root of 3, and length of 14. I can see this right away. We have 7, which is one length, and 14 is 2 times that length. This looks like it's the 30, 60, 90 formula. All we have to do is verify that the middle is the correct ratio, and it is. It's the short leg square root of 3 for the long leg. So it's not a 45, 45, 90 because, number one, there's no congruent sides. And that leaves us with either 30, 60, 90 or neither, but we've just proved that it can be the 30, 60, 90. Okay? So if you have any difficulties, be sure to contact me, and we'll see you soon.